Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials in Manufacturing Innovation. I've got a cool paper today. It fundamentally asks the question, if you're dealing with a nonlinear phenomenon, such as the transition in zones between two different metals that get joined together, why are we using a series of linear composition steps to adjust it instead of nonlinear ones, right? What we're talking about here is graded transition joints between different metals. Now, if you're not familiar with this, let me explain what's going on here. If you combine different metals like a ferritic with a martensitic stainless steel, you could be in a world of hurt, right? And the reason for that is you can have a really big gradient in the chemical potential of, say, carbon. Therefore, the carbon is going to find itself migrating from the ferritic region over to the austenitic region, resulting in this soft zone in the ferritic side, and that's going to have problems. It could be low creep resistance, for example. And so we don't want that, and we would love to avoid that. And one way that people have thought of to try and avoid this is to reduce the chemical potential by putting a series of intermediate layers between them. We call this creating a functionally graded transition zone between material A and material B. This can also help with other problems, not just diffusion. It can also help with thermal expansion mismatch. So it's pretty well known and it's been used for a while. However, when you get into the literature and look at it, you'll find that almost all of the published data relies on linear composition increments across the gradient zone, right? It'd be a nice smooth transition, but that transition isn't necessarily linear. It tends to be a nonlinear. So the authors here put forward a simple, fundamental question, which I really think is pretty clever. They say, our central question is this: given that a fixed composition path between two steels, P91 and 347H, can nonlinear physical thicknesses of these discrete composition zones be designed using the ICME workflow so as to minimize carbon chemical potential gradients and the residual stress across that joint in an actual additively manufactured material using DED. And then, so they're going to use nonlinear segments, but how do they define those segments? Here, this is pretty cool. They actually take inspiration from classical mechanics. They're going to use something called the brachistochrone curve. That comes from the Greek shortest time. Basically, this is comes from Bernoulli calculating the curve of fastest descent under gravity, right? Essentially, they're going to have a series of layers, but they're not going to have the same thickness, right? The thickness is going to become a design parameter that they can specifically explore to see what gives the best outcome. And the way that they're going to explore that is with ICME. Now, for readers of this journal, you're probably familiar with the ICME method, but just recapping, it essentially is going to rely on different calculation techniques working in synergy with one another across lengths and scales and different phenomena. So we have CalFAD, for example. We're going to use this to calculate the phase stability, the carbon chemical potentials, as well as the thermal expansion. And then we're going to use, in this middle box here, the modeling for FEM and diffusion. To get FEM model, we have to do the finite element method, of course, to get the mechanics, the stress out of this. And then to get diffusion, they're going to use the Dictra simulations to get diffusion simulated. And together, they should be able to then use this in a design framework. Ultimately, they're going to compare a couple different designs. Here's the linear designs, T1 and T2. You can see that those separations are always going to be the same. You can change the number of layers, but you're going to just keep the thicknesses uniform across it. Now compare that with these brachistochrone-inspired nonlinear layers, where you've got a thicker layer, and thinner and thinner and thinner and thinner. And these are going to be the comparison against which we're going to see whether this is actually a valid approach. Okay, the first results I want to point out are shown here in figure 4. You're seeing on the y-axis your chemical potential across this transition zone for these 4 different types of graded transitions. And what you'll notice if you look at, say, the chemical potential gradient for T4, the graded one, it is the smoothest, much smoother carbon chemical potential profile, which means that you would expect to see less carbon depletion, which you do, in fact, see less carbon depletion for this one across the P91 interface. In fact, it actually had 10% less carbon loss and a shorter transition zone than the linear designs. So this should translate to better performance and a lower fabrication cost. And the second thing I want to show here is this figure where they're actually showing, again, the design on the left, what they expected, and on the right, you're actually seeing the transition profile, where you can actually see the residual stress that they were able to get the improvement, like less diffusion, less carbon loss, and they didn't get higher residual stress, which is important because you would expect that to be a bit of a trade-off between those two things. Here you're able to get the diffusion benefit without paying any mechanics penalty, which is exciting. When you look at these transition curves shown on the far right, you see that it actually works. You essentially do have this nonlinear design giving you the hardness across the material, across the graded zone, and a defect-free transition region, as you see in the micrograph there. So ultimately, what I think we see in this paper is a powerful demonstration of the ICME method, a clever approach of tackling a fundamentally nonlinear problem with a series of nonlinear solutions. And I hope you'll check it out in the latest issue of IMMI.